This is Module 6, Lesson 1. We are going to talk about ions now. We have already begun to mention ions in the last module when we talked about cations and anions with the metals and the nonmetals, and we kind of introduced this idea just a little bit. We're going to dive more deeply into it as we go because we're going to have to start talking about ionic bonding, and that's made out of ions, so we really should know what ions are. So first and foremost, let's talk about valence electrons, because these are what make ions. The valence electrons are the electrons in the highest occupied energy level. And occupied energy level just means it's the highest energy level that has any electrons in it. It doesn't have to be full. So if you look at what we have here on the screen, you'll see that we have right here, you have that the number of valence electrons decides the chemical properties. So that's a reason that these are very important, because the closer that they are to having the number of electrons of a noble gas, kind of the crazier they get. The representative groups are going to be our A groups, and I'll show you that in just a minute. It's where their group number equals the number of valence electrons. So here's an example of that. If you look right here, let me get to it in pen here. If you look right here, you will see that you have A's up here on the top of the table and you have B's. The ones that have A's, the Roman numeral that goes with it represents the number of valence electrons. So like these have 1 valence electron. This group, the alkaline earth metals, they have 2, which matches up right there. When you get over here, it doesn't work that way anymore. These have 3, 4, 5, 6, 7, and 8. Now, you can just use these numbers. I guess you could memorize this pattern, but it'd be a lot easier just to know to use the Roman numerals. The reason that it doesn't work down here is because the transition elements vary in the number of valence electrons that they have, so there's no predictable pattern to it. So what they'll do with these is they'll have to tell you. So if you have a symbol like iron and they put a Roman numeral beside of it, that Roman numeral tells you how many valence electrons it has. That iron has 1. This iron would have 2. All right, so if it's anything from one of these B-labeled groups, and remember that also includes the 2 groups down at the bottom, the inner transition elements, then you would have to have a Roman numeral. Otherwise, you have no idea. Okay, there are a couple of exceptions to this. We'll learn those in a little bit. So back to this. Let's see how this works exactly. Here's an example from group 1A. All right, here's the electron configuration of sodium. The highest energy level mentioned here is 3. Well, in energy level 3, it has 1 electron, so that would be its valence electron. It has 1 valence electron. Here's an example from group 7. You would expect it to have 7 valence electrons. So let's see, bromine, here's its configuration. Its highest energy level mentioned in the configuration is 4. It's split up, that doesn't matter. The 4th energy level has 2 plus 5, that is 7 valence electrons, exactly what we would expect. And this is true of all of the A groups. Now, okay, we've looked at that for just a little bit here. We're going to move on to some other things. Let's talk about how the atoms make ions. They make ions to achieve the octet rule. The octet rule tells us what they're going to do. It says that they will form compounds to try to get the electron configuration of a noble gas. Say what? Let's go back to our periodic table for a second. All right, let me clear this off of there. And let's use us an example of, let's just do sodium. I have sodium mentioned on there. Okay, so maybe I won't clear that off of there. You know, my PowerPoint and I sometimes have issues. So we'll just leave that up there. I give up. Let's talk about sodium here for a second. It's my example on the next page. Sodium has 11 electrons, right? It has 1 valence electron. And the closest noble gases to it, there's argon over here, and there's neon right here. Neon is the closest. Neon has 10 electrons. It just has 1 less electron than sodium does. So what sodium would really like to do in life is it would love to get rid of that extra electron, its valence electron, and it would love to become like neon. So that's exactly what it does. Here is sodium's regular configuration with that one pesky electron that is keeping it from being like neon. Here's neon's configuration. So here's what happens. Sodium takes this electron and goes, bye, see you later, and it gets rid of it. So what does that do? It makes it have a +1 charge. Okay, so face-to-face kids, they usually get kind of confused at this point. How does it have a +1 charge? And why didn't sodium turn into neon when it did that? Well, remember this. Remember elements are defined by the number of protons? Sodium has 11 protons. This ion of sodium, y'all, it still has 11 protons. We didn't get rid of a proton, we got rid of an electron. This sodium up here, it had 11 electrons. Well, what did that do to it? That made it neutral. It had 11 positives and 11 negatives, so it didn't have a charge at all. That's why there's nothing written up here. But this sodium, it kept its 11 protons and it got rid of an electron, giving it 10. That gives it a +1 charge. Now, I don't know about y'all, but I'm not doing this much math each and every time that I do this. So I will just simply know that if it loses one electron, it'll have a +1 charge. If it loses 2 electrons, then it'll have a +2 charge. They're always opposite from each other. So you can come back to this and you can kind of start to make some generalities about what you know. Oh, hallelujah, we get a different color here. So if these all have 1, we learned in the last one that metals lose and nonmetals will gain. So if metals lose, if these lose 1, they become +1. If this loses 2, then these will be +2s. Okay, remember you have a dividing line right here of the stair step. So our stair step is our boundary between the losers and the gainers, so to speak. If this right here, the metals, which are, it's aluminum and down, if these have 3 valence electrons, they will lose them and become +3. These two right here have 4, they'll lose them and become +4. This one has 5, so it can become a +5 because it'll lose all 5 of them. Now, why didn't I include these? Because they're metalloids. And what we're going to see here is that metalloids tend to act like nonmetals. They become anions. So what they do is they gain. They are closer to 8 by gaining than they are by losing for the most part. So here's chlorine's electron configuration right here. What it does, if chlorine is, whoops, wrong way. If chlorine is right here, here's chlorine, the closest noble gas is argon. If it could get just one more electron, it could have argon's configuration. And that's exactly what it does. It gains 1, giving it a -1 charge, and it has the noble gas configuration that it's looking for. Same way over here. Chlorine as a regular ion had, what was it, 17? I think, yeah, has 17 protons and has 17 electrons. That's as a neutral atom. As an ion, it had 17 protons, but remember it gained 1. It has 1 more electron than protons, so it becomes a -1. Now let's work on charges for the nonmetals. Metalloids act like nonmetals. So if this one has 3, it's not going to lose 3. It's going to gain 5. Just count how many it needs to get to 8. 1, 2, 3, 4, 5. So this one would be a -5. These have 4 right here, so they would be -4s. These right here that I didn't highlight earlier, they have 5. They would be -3s. These would be -2s. -1s, and then these just, they don't have a charge for the noble gases because, well, they've got 8. They've got what they're looking for. Now, an exception, helium right here does not have 8 valence electrons. It only has 2, but it is still content with 2 because its first energy level is full. Remember, the first energy level only has an S sublevel, and it has it packed full of 2 electrons. It is content with 2. Okay, so let's talk about Lewis structures for just a second. Lewis structures are a simplified way of doing this. Like, we do not want to go around having to write all of this out. So the way that we can do it is with Lewis structures. The way I want you to think of a Lewis structure is of a symbol. So I'll let X be my symbol. And I want you to imagine that there's a box around the symbol. And around this box, we can fill in any of these 8 circles with electrons. All right. Now, we're just going to start. I'm going to do this row right here. I'm going to start with lithium, and I'm going to do the 8 A's that are in there. We can't do the B's because we don't know how many they have without someone telling us. So if we start with lithium, if you had 1 valence electron, you would just fill in any one of these circles that you wanted to. So I'm going to do this. This would be the Lewis structure for lithium. Put a dot to the left of it. You could put it on top, the bottom, or the right. It doesn't matter. There's lithium's Lewis structure. Okay. Now, what about beryllium? Beryllium has 2. It's in group 2A. All right, I would prefer that you not put the 2 together. Remember when we did the off-ball diagrams, we said that they would not share a room until they absolutely have to. So I would prefer that you spread them apart. Now, I would even prefer that you put them on opposite sides from each other. I'm not going to like have a coronary if you put them, like one on the top and one on the left. But if you really want to go for broke and do this as right as I think you could possibly be, then put them opposite from each other. You could also do it with one on the top and one on the bottom, but spread them out. Our next A would be boron right here. Boron has 3. You don't have any choice but to put them side by side, but you could put them anywhere you wanted to. You could do top, left, bottom, bottom, left, right, as long as you draw 3 dots and 3 dots only. Carbon has 4. So as you might be figuring, we can put 1 on each side, and that's as much as we can spread them out and kind of give them their own rooms. Now, when we get to nitrogen, you're not going to have a choice but to buddy somebody up because this one has 5. So you can put the pair on any side that you want to. So you should have a pair of 2 and 3 singles. Oxygen is going to have 2 pairs of 2. So as you can maybe imagine, I do opposites. I put the pairs opposite each other and the singles opposite each other. You could put the pair on the sides and the singles on the top and bottom. However, fluorine is next up, and you're only going to have 1 single electron and 3 pairs of 2. You can put the single one wherever you want to. Last but not least is neon. And if it's got 8 electrons, you would have to pair them all up. Okay, so this gives you an idea of how it would look if you had anywhere from 1 to 8. You cannot have something with 9 valence electrons. You either have none or you have 8. All right, a word about helium, since it's our exception here. If you did heliums, it would be proper to put them side by side because they are together. Remember doing the off-ball diagrams? If you drew the arrows, there's only one box to represent the one S, and you would put them together, so it's okay to go ahead and double them up right there. Okay, so let's talk about a couple of other things, and I'm going to do some of your practice work with you. Cations have a positive charge. They lose electrons. You can read the rest of this. I don't think you need me to read it to you. I do think it's important to stress that metals are the losers, okay? You can pause it and write the rest of this down. All right, the name stays the same. Pay attention to that. We just slap the word ion on the end of it. Anions, again, you can read this, so pause it and read through it. It's nonmetals, and there are gainers, okay? The endings change to "ide." This is the metalloids too. So chlorine becomes chloride, fluorine becomes fluoride. You do change the endings, and then you have a name for the halogens, which is the halides. So I'm not spending time on that. You can just read them right. So let's do some examples. This is your practice paper. You have the same first 4 problems that I have here because I wanted to do them with you. This is what we would do in my face-to-face classes, so put up with me on video longer. You should be able to use your reference table to figure out the answers to some of these, and I'll tell you how I know each thing. So if you have questions later, come back to this. Lithium has 1 valence electron. How do I know? It's in group 1. The Lewis structure, actually we just did it. It would have 1 dot on any side that you choose to put it. It is a metal because it's to the left of the stair step. It loses electrons. I know this because I have simply memorized it. Now, I'm going to have to use the stuff that I know to figure out this part. If I know that lithium loses, then I'm going to ditch this one dot and not draw it, and I'm going to give this thing a +1 charge. How do I know that it has a +1 charge? Because I know that if it loses one electron, it has a +1 charge. It'll just be the opposite. You subtract one over here, you add one for the charge. The name. Well, I've memorized that the positive ones, they don't change their names. We just slap the word ion on the end of it. So that's called lithium. So I write lithium, and then I add the word ion because this is plain old lithium. This is a lithium ion. Xenon. Well, it has 8 valence electrons according to my reference table because it's in group 8A. The Lewis structure of that is going to have dots all the way around. We just did this one too. Is it a metal or a non-metal? Non. Does it gain or lose? Trick question. It doesn't do any of those because it's already met the octet rule. It has its 8. The Lewis structure of the ion. Nah, not applicable. Doesn't do that either. That's why it's noble. It's snooty. It doesn't want to gain. It doesn't want to lose. It just wants to be left alone. The name of the ion doesn't have one. Doesn't apply again. Okay. What about this one? Well, why has it got this number? Because it's from a B group. Remember, it's a transition metal. The only way for me to know how many valence electrons is if they tell me with that Roman numeral. I like these. It's less work. It has 1. How do I do this? The same way I did the lithium. Put the dot anywhere you want to. This time I feel like putting it on the top. Let's be a rebel there. It's a metal. It loses because metals are losers. And what do I know? If it loses 1, then it'll become a +1. Now naming this thing. I don't just call it iron. I call it an iron 1 ion. When you are naming the transition metals, you must name it with that Roman numeral because otherwise nobody else knows how many valence electrons it had and they'll be all messed up. Hydrogen. Hydrogen has 1. It is in the first group. It has 1. So it would be H. Oh, I started to put HE. We'll just put my dot there. It's H with a dot. Now, it's a non-metal. Lives with the metal family, but it's a non-metal. And this is kind of tricky here. It can act both ways. Since it's a non-metal living in a metal family, it can lose and it can also gain. I'll show you both of these. So if I'm capable of drawing a straight enough line, I'm kind of proud of myself. Look at that. Go me. If it loses, then it'll become H plus because it only had 1. You can do this without the 1, by the way. You can just do H plus or you can do 1 plus. And we would call it a hydrogen ion because when they lose, we don't change the name. If it gains, it's close to helium. So it would gain 1 and it would have 2 dots and then it would become a -1. We would put the -1 on there. And usually when they gain, we put brackets around it just to indicate that the whole thing has a negative charge. And I wrote helium. That is not what I meant to write. I'm like writing and talking and like not paying attention. So if I mess up and I don't catch it in a video, y'all should make sure to tell me. Like come back in the comments for the lesson or something and be like, you screwed up. It won't be the first time. All right, here, let's redo this. H with 2 dots, and then it's got a -1 charge. When we do the anions, they change their endings to "ide." So instead of hydrogen, it would be hydride ion. All right? So why did I do this one? Because it's tricky. It's the only one that does this. There are not others. Everything else will either gain or lose or, like it'll be cut or dry. But this is kind of a tricky situation, and I wanted to do that for you. Now, when we get to compounds, how do we know which one it's acting like? Well, if you see it first, like here's these two. See on this one, hydrogen comes first, then it's acting as a metal. And if it comes second, then it's acting as a non-metal. So you can tell by the placement of where it's at, okay? We'll do more of that later. Okay, so moving on for just a second, one more thing, and then you get to do some practice with all of this. I want you to show the ionization of these, like how they become ions with a chemical equation is something that you're expected to do, and we do this multiple times. So all you're doing is taking what you have already said happens. We've done sodium and chlorine, and you're just writing it out. Like sodium falls apart into a sodium ion, and here's the electron that it gave away to become this ion. Magnesium would lose 2 electrons, so we show it losing the 2, but then you have to show it with a +2 charge because that's what it is now that it lost 2. Chlorine gains an electron, so we're showing them together on this side, making it a Cl- ion over here. Oxygen would gain 2, making it an O2- on this side. So you may see these written out. Go ahead and give it a try yourself. All right, so it's practice time. This is another lesson where there's a lot of explaining involved and a lot for you to draw. Please, 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 please make use of office hours to get help with this stuff. If office hours does not suit your needs time-wise, I know some of you are working on Mondays or on the bus going home. And if you don't stay up as late as I'm doing it on Tuesdays and Thursdays, then you need to let me know that you need another time. And we could always set up a different time or change one of them to meet the needs of everyone. So you also have the Q&A. Please post your questions there. Best of luck to you and happy drawing.